Section: Introduction. We're introducing a method for identifying text generated by large language models, LLMs, which is effective even when no training examples from the LLM source are used, a scenario known as the zero-shot setting. Despite this challenging condition, our approach surpasses all open-source methods for detecting text from ChatGPT and competes favorably with commercial APIs, even though they use training samples from ChatGPT. Our detector's zero-shot nature allows it to accurately identify multiple different LLMs, a feat that existing solutions can't achieve. This ability is increasingly important given the growing use of LLMs for activities such as operating bots, creating fake product reviews, and spreading misinformation on social media platforms. These actors have access to a variety of LLMs beyond ChatGPT, making a zero-shot, model-agnostic detection method crucial for maintaining the integrity of social media platforms. Our proposed detector, which we've named Binoculars, operates by examining text through two lenses. First, we calculate the logarithm of the text's perplexity using an observer, LLM. Then, we calculate all the next token predictions that a performer, LLM, would make at each position in the text, and compute their perplexity according to the observer. If the text was written by a machine, these two perplexity values should be similar. If it was written by a human, they should be different. We'll explain this observation and show that it's enough to build a robust zero-shot detector, which we'll test extensively across various text domains. Detecting machine-generated text is a crucial first step in mitigating the potential harm caused by generative AI. Applications that benefit from this include tracing text origins, investigating spam and fake news campaigns, and analyzing training data corpora. While early efforts to detect machine-generated text were successful with primitive models, the rise of transformer models for language modeling has rendered these methods ineffective. Detectors can be divided into two main categories. The first includes trained detection models, where a pre-trained language model is fine-tuned for the binary classification task of detection. The second category includes methods that identify statistical signatures characteristic of machine-generated text. These methods require little or no training data and can easily be adapted to newer model families. From a theoretical perspective, fully general-purpose models of language would be impossible to detect. However, even models that are very close to this ideal can technically be detected given enough samples. The relative success of detection approaches, such as the one we propose, provides evidence that current language models are imperfect representations of human writing and can therefore be detected. A key question is how to evaluate detectors effectively. Many works focus on accuracy on balanced test sets and/or the area under the receiver operating characteristic curve, AUC, of their proposed classifiers, but these metrics are not well suited for the high-stakes question of detection. Detectors should have low false positive rates across a wide distribution of human-written text to truly reduce harm. In this work, we focus on baselines that function within post-hoc, out-of-domain, zero-shot, and black box detection scenarios. We compare detection performance across various datasets using the state-of-the-art open-source detector Ghostbuster, the commercially deployed GPT-0, and Detect-GPT. We also evaluate the reliability of binoculars in various settings that constitute edge cases and crucial deployment behaviors that a detector based on binoculars has to take into account. Section Summary. We present a method called Binoculars for detecting machine-generated text, specifically language model text, in the zero-shot setting. Our approach outperforms existing open-source methods for ChatGPT detection and is competitive with commercial APIs, making it critical for social media moderation and platform integrity assurance. Binoculars works by computing the perplexity of the text using an observer language model and comparing it with the perplexity of next token predictions made by a performer language model. This simple observation allows us to build a strong zero-shot detector that can detect multiple different language models with high accuracy. Section: Binoculars. How it works. Our method, which we've named Binoculars, is inspired by the way we use two different language models to examine inputs. It's widely recognized that perplexity, a common benchmark for distinguishing between machine and human language, isn't enough on its own. This has led to a general disregard for methods based on statistical signatures. However, we suggest using a ratio of two scores, one being a perplexity measurement and the other being cross-perplexity, which is a measure of how unexpected one model's predictions are to another model. This dual model mechanism forms the foundation of our broad and precise detector. We demonstrate that this mechanism can detect a variety of large language models, even those that are unrelated to the two models used by binoculars. To understand the basics, let's consider a string of characters. This string can be broken down into tokens and represented as a list of token indices by a tokenizer. Each token has an ID, which corresponds to an entry in the language model's vocabulary. Given a sequence of tokens as input, a language model predicts the next token by outputting a probability distribution over the vocabulary. We use the term log perplexity to refer to the average negative log likelihood of all tokens in a given sequence. Essentially, log perplexity measures how unexpected a string is to a language model. As we've mentioned, perplexity has been used to detect large language models, as humans tend to produce more unexpected text than these models. This makes sense, as log perplexity is also the loss function used to train generative large language models, and models are likely to score their own outputs as expected. Our method also measures how unexpected the output of one model is to another. We define the cross perplexity, which takes two models and a string as its arguments. So, why do we need both perplexity and cross perplexity measurements? It's not surprising that large language models tend to generate text that is expected to another large language model. However, because humans are different from machines, human text has higher perplexity according to a large language model observer. This might make it tempting to use raw perplexity for large language model detection, as high perplexity is a strong sign of a human author. But this approach falls short when we consider handcrafted prompts. Prompts have a strong influence over the resulting text, and prompts are typically unknown to the detector. For example, the prompt 1, 2, 3 might result in the very low perplexity completion 4, 5, 6. But the prompt, "Can you write a few sentences about a capybara that is an astrophysicist?" will yield a response that seems more strange. In the presence of the prompt, the response may be expected, low perplexity. But in the absence of the prompt, a response containing the unusual words, capybara, and astrophysicist, in the same sentence will have high perplexity, leading to the incorrect conclusion that the text was written by a human. We refer to this dilemma as the Kabara problem. In the absence of the prompt, large language model detection seems difficult and naive perplexity-based detection fails. Our solution, Binoculars, addresses the Kabara problem by providing a way to estimate the baseline perplexity induced by the prompt. By comparing the perplexity of the observed text to this expected baseline, we significantly improve large language model detection. Language models are known for producing low perplexity text relative to humans, so a perplexity threshold classifier seems like an obvious detection scheme. However, in the era of large language models, the generated text may have a high perplexity score depending on the prompt specified. To adjust for prompts that yield high perplexity generation, we use cross-perplexity as a normalizing factor that intuitively encodes the perplexity level of next token predictions from two models. Rather than looking at raw perplexity scores, we propose measuring whether the tokens that appear in a string are unexpected relative to the baseline perplexity of a large language model acting on the same string. A string might have properties that result in high perplexity when completed by any agent, machine or human. Yet, we expect the next token choices of humans to be even higher perplexity than those of a machine. By normalizing the observed perplexity by the expected perplexity of a machine acting on the same text, we can arrive at a detection metric that is fairly invariant to the prompt. We propose the Binoculars score as a sort of normalization or reorientation of perplexity. Specifically, we look at the ratio of perplexity to cross-perplexity. Here, the numerator is simply the perplexity, which measures how unexpected a string is to one model. The denominator measures how unexpected the token predictions of a second model are when observed by the first model. Intuitively, we expect a human to diverge from the first model more than the second model diverges from the first model, assuming the large language models are more similar to each other than they are to a human. The Binoculars score is a general mechanism that captures a statistical signature of machine text. We show that for most obvious choices of models, Binoculars separates machine and human text much better than perplexity alone. Importantly, it is capable of detecting generic machine text generated by a third model altogether. Interestingly, we can draw some connection to other approaches that contrast two strong language models, such as contrastive decoding, which aims to generate high-quality text completions by generating text that roughly maximizes the difference between a weak and a strong model. Speculative decoding is similar. It uses a weaker model to plan completions. Both approaches function best when pairing a strong model with a very weak secondary model. However, as we show, our approach works best for two models that are very close to each other in performance. In the remainder of this work, we use the open-source models Falcon 7B model and the Falcon 7B Instruct. The full set of combinations of scoring models used can be found in the appendix. Section Summary. The approach called Binoculars uses two language models to detect machine-generated text. It measures the ratio of perplexity and cross-perplexity, where perplexity measures how surprising a string is to one model, and cross-perplexity measures how surprising the token predictions of another model are to the first model. By comparing the observed perplexity to the expected baseline perplexity induced by the prompt, Binoculars provides an improved detection score for distinguishing between machine and human text, even when handcrafted prompts are involved. Section: Accurate zero-shot detection. In this section, we'll discuss our newly proposed scoring system and how we've used it to create a zero-shot language model, LLM, detector, which we've named Binoculars. This tool allows us to identify text that has been generated by a machine across various domains. Our primary focus in this evaluation is to detect machine-generated text from a modern LLM, which is typically produced without any specific detection mechanism in mind. We begin our experiments using several datasets that have been previously used in LLM detection research. We compare our results to the most recent baseline, a method called Ghostbuster. The creators of Ghostbuster also introduced three datasets that we've included in our study: writing prompts, news, and student essay. These datasets are balanced, containing an equal number of human-written and machine-written samples, with the machine samples being produced by ChatGPT. We've also created several of our own datasets to test our ability to detect text generated by language models other than ChatGPT. We've used human-written text from sources like CC News, PubMed, and CNN, and generated machine-written text using Llama 2-7B and Falcon 7B. We took the first 50 tokens from each human-written sample and used them as prompts to generate up to 512 tokens of machine output. We then removed the human prompts, leaving only the machine-generated text for our datasets. We also used the Orca dataset, which contains several million instruction prompts and their machine-generated responses from chat versions of GPT-3 and GPT-4. This dataset allows us to test the reliability of our method when detecting instruction-tuned models and to quantify detection differences between GPT-3 and GPT-4. Since detectors are essentially binary classifiers, we use standard binary classification metrics. While it's common to look at ROC curves and use the area under the curve, AUC, as a performance metric, we argue that these metrics alone are not sufficient when measuring LLM detection accuracy. In high-stakes detection settings, the most significant issues often arise from false positives, i.e., when human text is incorrectly labeled as machine-generated. Therefore, we focus on true positive rates, TPR, at low false positive rates, FPR, and adopt a standard FPR threshold of 0.01%. We will present F1 scores and AUC values only for comparison to previous publications, but we prefer to focus on TPR values at low FPR as a key metric. Using several datasets, we compare the AUC and TPR of binoculars to Ghostbuster, GPT-0, and Detect GPT. We note that these comparisons are biased in favor of GPT-0 and Ghostbuster when using machine samples from ChatGPT, and in favor of Detect GPT when using samples from Llama models. Our score-based detector has just one tunable parameter, a threshold to separate machine and human text, which we preset using reference data. We set this threshold using a combination of training splits from all of our reference datasets, which are generated using ChatGPT. We also compare detectors on Llama 2-13B and Falcon 7B generated text with prompts from CC News, CNN, and PubMed datasets. All of these datasets have an equal number of human and machine-generated text samples. We optimize and fix our threshold globally using these datasets. We also compare our performance with Ghostbuster using only samples from CC News, CNN, and PubMed to choose our threshold. This is to ensure that we meet the Ghostbuster definition of out-of-domain. We show that Binoculars outperforms Ghostbuster in the out-of-domain setting, which is the most realistic and includes evaluation on datasets other than Ghostbuster's training data. Both Binoculars and Ghostbuster improve with more information, but the advantages of Binoculars are even clearer in the few token regime. Finally, we demonstrate that our detector is capable of detecting the output of several LLMs, such as Llama and Falcon. We also observe that Ghostbuster is only capable of detecting ChatGPT, and it fails to reliably detect Llama-generated text. Section Summary. In this section, the authors evaluate their proposed score and build a zero-shot language model, LLM, detector using it. They use various datasets, including those from the LLM detection literature and datasets they generate themselves, to evaluate their detector's capability in detecting machine-generated text from different language models. They argue that traditional metrics like AUC and F1 scores are inadequate for measuring LLM detection accuracy and instead focus on true positive rates at low false positive rates as a key metric. They compare the performance of their detector, Binoculars, to other detectors like Ghostbuster, GPT-0, and Detect GPT, and show that Binoculars outperforms Ghostbuster in the out-of-domain setting. They also demonstrate that Binoculars can detect the output of different LLMs like Llama and Falcon, while Ghostbuster is only capable of detecting ChatGPT. Section: Reliability in the Wild. Let's delve into the practical performance of our tool, Binoculars, in real-world scenarios. The main point we want to emphasize here is that Binoculars is essentially a detector of machine-generated text. In simpler terms, it predicts the likelihood of a given text being produced by a similar language model. This has significant implications for various situations, such as dealing with memorized samples, text from non-native speakers, modified prompting strategies, and edge cases. We'll discuss all these aspects in detail in this section. First, let's look at how Binoculars performs with different types of text sources. We tested it on a variety of settings beyond natural English language, using the multi-generator, multi-domain, and multilingual M4 detection datasets. These datasets include samples from sources like Archive, Reddit, WikiHow, and Wikipedia, and in various languages like Urdu, Russian, Bulgarian, and Arabic. The machine text samples in this dataset were generated using ChatGPT. We compared the precision and recall of Binoculars with 4 other baseline methods and found that Binoculars performs well across different domains and languages. These baseline methods include Roberta fine-tune to detect LLM text, logistic regression over giant language model test room, LRGLTR, stylistic, and news landscape classifiers, NELA. Next, we evaluated Binoculars on samples from languages that are not well represented in the standard LLM pre-training data, Common Crawl. We found that the false positive rates remained low, which is a good thing from a harm reduction perspective. However, Machine text in these low-resource languages is often misclassified as human-generated. While this is a limitation, it's important to remember that Binoculars is designed to detect whether text may have been generated from a similar language model. Since the Falcon models we use are not very good at generating text in these low-resource languages, the ChatGPT-generated text is unlikely to be flagged as machine-generated by our score. We believe that using a stronger pair of multilingual models could improve Binoculars' ability to detect machine-generated text in these languages. A significant concern about LLM detection algorithms is that they might be biased against non-native English speakers, often misclassifying their writing as machine-generated. To test this, we analyzed essays from Essay Forum, a website for ESL students to improve their academic writing. We compared the distribution of Binoculars scores across the original and the grammar-corrected samples. Interestingly, Binoculars achieved equal accuracy of 99.67% for both corrected and uncorrected essay datasets. This shows that Binoculars is not sensitive to this type of shift. Lastly, we looked at how Binoculars handles memorized text. For instance, famous quotes that appear many times in the training data are often classified as machine-generated. We tested Binoculars on several such examples, including the U.S. Constitution, a document that is largely memorized by modern LLMs. Binoculars scored it at 0.76, indicating it as machine-generated. While this might seem surprising, it's consistent with the nature of a machine text detector. Depending on the application, classifying memorized text as machine-generated could be either acceptable, for example, in plagiarism detection, or undesirable, for instance, when removing LLM-generated text from a training corpus. Section Summary. The section discusses the reliability of Binoculars in real-world scenarios. Binoculars uses a machine text detector to predict the likelihood that a given piece of text was generated by a language model. The detector's performance is evaluated across various text sources, including different languages and non-native speakers, and it shows good generalization. However, when it comes to low-resource languages, the detection is limited due to the capability of the language models used. Additionally, Binoculars performs well in detecting memorized text, which can be both human-written and machine-generated. Section: Modified Prompting Strategies. We've been testing our tool, Binoculars, on the OpenOrca dataset, which includes machine-generated content from both GPT-3 and GPT-4. This dataset is a great testing ground for Binoculars, given its diversity. We found that Binoculars could identify 92% of the GPT-3 samples and about 89.57% of the GPT-4 samples when we used a global threshold derived from reference datasets. We only report accuracy here because we're dealing with machine-generated text only. The OpenOrca dataset also gives us prompts that help us understand how Binoculars reacts to changes in prompts. Some detection methods can be tricked by simple changes to prompts, which can result in stylized text that differs from the standard output. To test this, we used Llama 2-13b chat and prompts designed to alter the style of the output. For example, we asked Llama 2-13b chat to write in the style of Carl Sagan, to avoid any mechanical or robotic-sounding words, or to write like a pirate. We found that these stylistic changes didn't significantly affect the accuracy of Binoculars. The biggest change we saw was when we asked for pirate-style output, which only reduced the sensitivity, or increased the false negative rate, by 1%. We also wanted to see if random mistakes, hash codes, or other types of random strings could lead our model to false positives. To test this, we generated random sequences of tokens from the Falcon tokenizer and scored them with Binoculars. We found that Binoculars confidently scored these as human, with an average score of about 1.35 for Falcon. Humans have an average of around 1. This is expected, as trained language models are unlikely to generate completely random sequences of tokens. We've developed Binoculars to detect language models in situations where no data is available from the model being detected. Our detector works without needing access to the specific model used for generation or example data from it. We think this is possible because modern language models are very similar, as they all use nearly identical transformer components and are likely trained on datasets made up mostly of common crawl data from similar time periods. As more and more open-source language models become available, the ability to detect multiple language models with a single detector is a major advantage of binoculars. However, our study does have some limitations. Due to limited GPU memory, we didn't perform broader studies with larger, 30B+ open-source models in our detector. We also focused on detecting machine-generated text in normal use, and didn't consider deliberate attempts to bypass detection. We also didn't look at other non-conversational text domains, like source code. We've provided details on all the datasets we used and the exact method we used in this work. We've also provided code to replicate our detection score implementation. We note that comparisons to commercial detection APIs, like GPT-0, are based on API evaluations from September 2023, and may not be reproducible in the future. This highlights the importance of transparent, open-source solutions. Language model detection could be a key technology to reduce harm, whether it's to monitor machine-generated text on internet platforms and social media, filter training data, or identify responses in chat applications. However, we need to make sure that detection mechanisms actually reduce harm, rather than increase it. We've conducted an extensive reliability investigation of binoculars, and we believe it's a significant step forward in terms of reliability. But this is just the first step in deploying language model detection strategies, and developers still need to carefully verify the impact on their systems. We also want to stress that just because language model detectors exist, it doesn't mean they should be used in all scenarios. We also want to make it clear that we're focusing on detecting machine-generated text that naturally occurs, as generated by language models in common use cases. We know that no detector is perfect and we can't guarantee performance in situations where someone is trying to trick our system. We've conducted a thorough evaluation across a wide variety of test sources, but we acknowledge that directed attempts to bypass our classifier might be possible, as is often the case with systems that rely on neural networks.